Okay, we're gonna get started. I'd like to welcome Matthew Rocklin from Anaconda for the next talk.
Great, thank you, Peter. Thank you so much for having me here. So my name is Matthew Rocklin. I'm an open source software developer at Anaconda. Anaconda is a for-profit company inside the more sort of data science oriented part of Python. So if you're familiar with libraries like NumPy or Pandas or scikit-learn, that's sort of the space of tools that we sort of care about. My job is to improve the performance of those tools. So I operate entirely in the open source. I mostly care about parallel and scalable computing, mostly with a library called Dask. And most talks that I give are about Dask. This talk is going to be a little bit different. It's going to be a little bit more high level, a little less technical. And we're talking about collaboration I've had the privilege to being a part of with tools like XArray and JupyterHub to help a lot of atmospheric scientists and oceanographic scientists interact with large-scale data sets on the cloud. That collaboration goes under the name Pangeo, and it's welcome to any people who might be in the audience. I mostly talk to scientists, and I mostly talk to people who understand hardcore numerical computing. This group is, I think, different. I think it's more mixed, which I really like coming to PyCon. So my goals are a little bit different here. So we're talking about a few Python tools, ones I just mentioned and a couple others, to do atmospheric and oceanographic science. I'm assuming people here don't do these sciences. Any oceanographers or atmospheric scientists in the room? There's Felipe and a couple other person I don't know. Yeah, so it's a fun topic. So our goal is here to provide some context for scientific Python. People who aren't familiar with NumPy understand how it gets used. We want to sort of maybe attract some other scientific groups to this collaboration. It's been a really fruitful thing so far. I think we could expand. And I also want to encourage some non-science people to help out. So it turns out that doing science requires a lot of non-science skills. Many skills that I think are in the room, so please come and help. I feel like this has been my effort to reduce carbon in the world has been maximized by this effort, so please come on by. And also learn a little bit about the Earth's oceans. So, I know. Great. Slides are available on matthewrocklin.com/slides/pycon2018.html. Give it up for just a moment. Also tweet these slides in a moment. Okay. So, we live here, and we measure the Earth quite a bit. We have cameras in space. We also have other things in space, things like radar and LiDAR systems that do a variety of interesting scientific instruments that look down on us. We have ground-based observations. We have lots of things we measure. We also do simulations. So I'm going to switch to a video for a moment. This is a simulation of the Earth's oceans at some resolution, some high resolution. This is run, this is not an observation, this is a simulation. It runs in a giant supercomputer. This generates, I think, something like 2 petabytes of data every time it runs. And this helps us understand how the oceans and the atmosphere exchange heat amongst each other in fun ways. So you can see things here like a nice sort of stream coming off of Japan. I think if we sort of move forward a little bit, we'll see the Gulf Stream. So there's a lot of structure here, and understanding this structure is very important to understanding how we hope to continue to live on this planet. So first, we measure the Earth, either with observations or with simulation, and then scientists do a lot of analysis. They typically do this analysis in Python. Python is becoming the standard language to do this sort of work. So I'm going to do a quick demonstration of how people use Python to analyze this sort of data. I'm going to use a tool called XArray in a Jupyter notebook. So I'm going to assume some exposure, light exposure to Jupyter notebooks. It's a web page I go to. It's running on my personal computer. And I'm going to load some data with XArray. So I'm reading some data in the netcdf format. This is a great file format to look at a lot of gridded data. So a lot of this data isn't like a SQL database. It's not a bunch of records. It's a bunch of gridded data structures. So you might have, for example, the temperature on every point on the Earth at every elevation over time, and that might be a 4-dimensional data structure. You might also have the temperature and the pressure and the wind speed and the humidity, many different arrays that are related to each other. So this is maybe like images, but maybe more complex. So this is a relatively small data set, and it has the sea surface temperature, which has dimensions of latitude, longitude, and time. So I might, like with pandas, cut out the time coordinate and look at it, and we can see that it's going from 1960 to 2016. And I might do some small operation like min, and see that the earliest this data set goes back is 1960. So, but again, this is not necessarily pandas data, this is n-dimensional data. So here is the average of that temperature over time. We can see that it's hotter in the oceans near the equator, which is not a big surprise. But I was able to query that and do that reduction relatively easily. And so I'm doing sort of a high-level analysis, but using libraries like NumPy and pandas to do relatively efficient code underneath. When I do something else, we might select a time range, maybe since the millennium. We might take an average over the longitude, so we're just going to look at the latitude and time. Then we're going to subtract off the average over time. And this shows us the temperature of the ocean normalized on the northern and southern hemisphere. And you can see things sort of switch depending on where you are on the summers. So this is a sort of a modestly complex visualization we achieved by relatively small lines of code. Underneath the hood, this is still just using NumPy. So NumPy is a library to deal with gridded data structures, such as you might find in images or these higher dimensional structures. So people like NumPy, they like XArray. They've been doing this for a while. And so what are the tools we saw? We saw Jupyter Notebooks. We saw a NetCDF, a file format, and XArray, a computational engine that uses NumPy and pandas to do some queries on that. These are very common tools in that space. So I'm going to set a quick timer here. Okay. So we use NumPy and pandas to do efficient in-memory computation. This is using Python code to drive C code to run quickly. We also use matplotlib to visualize results. And this has been going on for a long time. Sort of familiar roughly with the scientific Python stack. These are sort of normal tools that you might be familiar with. XArray optionally uses Dask, a library I work on, so this works up to sort of the 10 gigabyte to 100 gigabyte scale on a single machine. And that's, again, sort of commonly done today. We're now going to step forward a little bit and see how well we can scale that out to larger data sets. Because remember, this video, with all the swirliness and intricate detail in it, comes in at petabytes. So that's megabytes, gigabytes, terabytes, petabytes. So you've got quite a ways to go till we get to something like this. Okay, so we use Jupyter Notebooks because scientists like to code interactively. They don't have a particular end goal that they're shooting towards. They need to iterate very quickly as they're searching. They're searching for whatever might be interesting in that data set. They can't write tests and then write to those tests. It's much more an interactive flow. It also runs in a browser, and more or less this is not particularly exciting for most people on their laptops. It's sort of I create a Jupyter server, I log into that server, everything's running locally. It could just as well have been a rich client application, they wouldn't have cared. We'll see that this is going to be very important when we switch to more distributed systems, when we create remote systems for them to work with. So running in a browser ends up being very important. And that's one reason why we really like Jupyter as we move forward. So let's look briefly at NetCDF and XArray. So again, these libraries manage collections of regularly gridded, homogeneously typed data, like NumPy, but they have many different arrays. So you might have a few arrays, like the temperature and the pressure, that might be three-dimensional. You might have other arrays, like the land cover or the elevation, that might be two-dimensional. You might have indexes and axes, like the longitude and time. And these libraries collect all of these different arrays into one cohesive unit, so you can do things like take an average over time, and it will average everything appropriately. You might also, if you go outside of this space, think about maybe movies. A movie might be a three-dimensional array of all the frames of the film with a time axis and two spatial axes, and then maybe an audio track also, with sharing the same time axis, but having maybe a channel axis for the different audio tracks. So this general technology happens to be very useful in this scientific domain. XArray uses NumPy for computation on the individual arrays, and uses pandas for the indexes. I want to quickly say here that this pandas tabular model only really works well for the coordinates on the sides. It doesn't work well for the actual gridded data inside, because that data is regularly strided, it's more gridded. It's hard to fit that into sort of a classic database model. So these tools allow scientists to analyze critical data quickly, which is we like, because they're actively fighting to keep the planet alive. So we should support them. But there's some challenges. Data sets are increasing rapidly. NASA's putting in satellites, and many other agencies, international governments, for-profit companies are putting a bunch of satellites into space right now. They're trying to generate amazing amounts of satellite imagery, which can really change how we understand our planet. At the same time, the average human user is becoming less sophisticated. We're getting far more students who are using these tools with far less training. Also, not just students, but also, emeritus faculty who have far less training in using Python. We need to lower the barrier to adoption. They're not able to spin up clusters, write MPI code. That's a challenge. So I'm going to show you a thing that we've been working on recently. If the internet works, hopefully go to live demo. If not, we'll switch to video. I'm running. Let's restart this for a moment. So I'm going to show you a website, pangeo.python.org. And you can log into this with your GitHub credentials. And I'm going to do a much larger analysis now. Thank you. This is using XArray again, but on some larger data. Here I'm going to connect to some data stored in the cloud. I think in total this is a few hundred gigabytes. It's not huge, but it's bigger than I want to work on my laptop. And we've read just some metadata. And so this data set is like the data set we saw before about sea surface temperature, but it now has many variables. We're going to look particularly at the sea level altitude, which is larger than what we had before. It's sort of a 10,000 by 1,000 by 1,000 array. And this is the sea level for a high resolution over a very long time. So this data set is going to be somewhat large, so we're not going to be able to work on it with our single machine. We're going to connect to Kubernetes. We'll talk about this a little bit. We'll talk about this more a little bit in the future, and we'll ask for maybe 40 workers. And this is using Dask, which again we'll talk about a little bit in the future. So we've got some workers, connect to that cluster, and now we're going to do something simple. We're just going to look for one day of that data and plot the result. So this is the sea level altitude. So again, this is sort of maybe how high the tides are or how high the ocean is relative to the land. And we see some interesting structure. We see in the equator, it's so red is higher, blue is lower. In the equator, it's relatively calm and uniform. Maybe on the windward side or on the east side of most land masses, we see a lot more variability. Right? Around the Cape here, there's a lot of churn. So this is just one day of data, and we have 10,000 such days or time points. So this particular array is around 70 gigabytes in RAM. Again, this is not large. People deal with larger things than this, but it's sort of something I can work with interactively for a conference talk. So let's do some more computation. Before I do that, I want to open up the Dask dashboard, which will help us understand how things are going. So I'm going to scroll up here a little bit. And this will give us a nice sort of visual view of what's happening on our cluster as we do some more serious computations. I'm going to scroll back down to where we were before. And we're going to do some more complex computations. We're going to take the average across spatial dimensions, take the averages across longitude, and then look at the variance over time. And what that's going to do, that's going to break up our computation into thousands of little small pieces that we can then run across a cluster. So on the right side of the screen, you're seeing the activity of those 80 cores. Every line here corresponds to the trace of one core as it loads some data, computes some averages, et cetera. And those are taking 100 millisecond Python functions that are running on various machines. And Dask is just coordinating all those machines to give us what we need. So this is showing us the activity of our cluster over time. And what that's doing is that's by doing all of these very small NumPy or very small pandas computations, it is completing for us a much larger aggregate computation, this averaging over various dimensions that we asked for. So now that that's done, took around 30 seconds, we can start doing some more, we can look at those results. I'm going to go full screen on the left here, just so the images can be a bit larger. So let's look at we average over the spatial dimensions, so we're just looking at the result over time. And here we can see the sea level average over the Earth over time. And so you can see the cyclic variability, just winter and summer, there's some, the Earth sort of breathes a little bit. You can also see a marked increase over time, so the sea level is rising. And this is interesting, right, because we didn't have to look up at an agency to find out this information. We just got to log into a website, look at the real data, analyze that data, and come to a conclusion. This is sort of takes out any sort of politics from the discussion, something that we can immediately go towards directly. Let's look at some more analyses. The thing that takes a long time here is actually plotting the result. The computation is all done. There we go. So this is the same analysis, but we've included latitude, so you can see how the sea level rise will change about southern or northern latitudes. And you can see that things change a little bit. It looks like there's some fine structure here around maybe latitude 38 or 37. Things still may be a little bit different in the north and the south. We might then also look at the variability of sea level over time. And we can see that on the eastern coasts of most continents, we actually see more variation. Right? So it might be the east coast of your continent has higher and lower tides than the west coast of your continent. And I don't know why this is. You have to ask an oceanographer. Maybe it's the winds or something like that. So again, we're doing science here, and we didn't really have to think that much about distributed computing or scale. It was all relatively intuitive, if you're familiar with XArray, which many of these scientists are. Okay, so you can do this too. This is available on pangeo.pydata.org, which is a JupyterHub deployment that has open access currently with GitHub. Please don't mine Bitcoin. When you might start mining Bitcoin, we have to start putting in access controls. But try it out. The Wi-Fi here is not necessarily the greatest, but you should try it out. Might take a couple minutes for things to spin up. So you can do the exact analysis I just did is available to you. You can do exactly that thing if you log in. So we use JupyterLab, we use JupyterHub, we use Dask, we use Kubernetes. Okay. So these tools are maybe a little bit newer than the ones we saw before, and we're going to see a little bit about why those matter. Talk about JupyterLab first. So here we have the classic Jupyter Notebook. Here we had JupyterLab. I think the style is a little bit nicer. I also like the keyboard shortcuts. I can restart and clear my notebook without ever really touching a mouse. Some other nice things. I've got a file browser. I can look around. I can look at examples, these different things. I also have a terminal. So JupyterLab is a much more fully featured development environment, much more so than the classic notebook. This didn't matter when I was on a single machine, but it really matters when I'm on a cluster. And I want to manage my software environments. I want to manage lots of things. Okay. Second, JupyterHub. So JupyterHub is one way to give many different users their own Jupyter server. So I'm stealing these slides from Carol Willing, who was generous enough to donate them to me. And so JupyterHub is a way to give many people a Jupyter server. So a notebook is a document, a software environment that's all served through web application. So a user looks at their monitor, that goes to their browser, and that goes to some HTTP server. Almost always this is running on their local machine. It doesn't have to, it can run somewhere else. What I would like to do, though, is I'd like to give a Jupyter server to many people. Everyone who logs in to pangeo.pydata.org gets their own Jupyter notebook server that's independent from everyone else. They have their own software environment, their own home directory. And JupyterHub handles all that for me. So I've got many users, they look at their laptops, they go through an HTTP proxy, they talk to the hub spins up a Jupyter notebook server on Kubernetes and gives them access to that server. We also saw Dask. So Dask is a library for parallel computing. This is what I work on. This is my sort of small piece of this collaboration. So this is designed to scale the existing Python data science libraries like NumPy, Pandas, or scikit-learn. Works in a variety of other contexts. I give a much broader talk about this topic at PyCon last year. If you care about parallel computing or scalable computing, you might want to watch that. But generally speaking, we're just using one part of Dask, XArray, which scales NumPy. XArray, if you recall, used NumPy for computation. DaskArray can scale NumPy computations. It takes many small NumPy arrays that might be distributed across a cluster and coordinates them to create one logical array. That creates a task graph, which Dask can then execute on parallel hardware. That's like the 30-second explanation of Dask. Probably no one got that. That's fine. But Dask gives you some parallel computing with a lot of Python code. We also use Kubernetes to manage both JupyterHub and Dask. So Kubernetes is a system that you can run on a cluster. It allows many distributed systems to share that cluster. So JupyterHub and Dask both want to create a bunch of machines, a bunch of processes running in my cluster, and Kubernetes is the thing that makes them share nicely. So what actually happens with this deployment that we have, which is very similar, you can make these things too. This is one example of what we built. So I have a bunch of machines. These are these blue boxes. And on one of those machines, I'm running JupyterHub. A user shows up, talks to JupyterHub, and JupyterHub gives them a Jupyter Notebook server, maybe on the same machine, maybe on a different one. That user then talks to the notebook. They import Dask. They ask for some Dask workers. And Kubernetes gives them some Dask workers as well. So now they're using the same cluster to both to have their notebook running in a single machine and many, many Dask workers at the same time. Another user might show up, might ask for another Jupyter notebook, and they might ask for even more workers. Here, Kubernetes is going to talk now to our cloud provider. We happen to be using Google, who's generously donated a bunch of money for us to run on their hardware. And Kubernetes will apply pressure upstream, and Google will now give us more machines to work with. We can then launch more Dask workers. The first user might go away. JupyterHub will nicely clean up things, and the cluster can scale down. So this is how we're using JupyterHub and Dask together with Kubernetes on the cloud, and it's been very effective so far. So we've run this service continuously for a few months. It showed up first in around January to a very small group of people. We've been increasingly expanding the service. And science users frequently scale up to sort of 1,000 core clusters. And things can scale up in that nice horizontal way, and they can come back down. As long as the science users are sort of judicious about cleaning things up when they go away, and we have various tools to help do that, we've been able to keep down costs. So it's cost us sort of thousands of dollars, which may be a lot to some of us, but is very, very low relative to your average distributed system running in some government lab. There's also no dedicated support staff, so we don't have to hire anyone to manage this. It seems to all work, more or less. So a few thoughts, a few comments about impact and community. This started with an NSF grant between some of the XArray developers that were working at Columbia University and NCAR, the National Center for Atmospheric Research, scientists at both of those organizations, and also Anaconda, where I work, a bunch of open source software developers, to make this sort of system. It's been a really good collaboration. It's been really nice having professional software developers working hand in hand with scientists, funded for government public need. This has been very popular with many other government agencies. If you go to pangeo.pydata.org, you'll see a lot of information about other groups that have come on, including other government labs. I particularly want to thank the UK Met Office, who's done a lot of work. Also groups like NASA, USGS, other various government organizations. And people regularly log in and do work. Let's go ahead and see if someone is doing work. The system, by the way, is completely insecure. Don't put anything up there. It can go down any time. There's very bad access controls. So here's people who've logged in so far. Some of these I recognize as being scientists, Kai Pak. Some of these I imagine are people from the audience. It looks like Kai Pak is also learning a lot of Dask workers. We've also, this is actually my favorite thing, we've gotten scientists to talk about science without talking about scale. So the example I showed you was incorrect. Someone showed up and said, hey, you're actually not accounting for the fact that the poles are a little bit different from the equator. You're not doing spatial averaging correctly. If you do that spatial averaging, you'll find that sea level rise has actually been a bit larger than you're anticipating. There's a long conversation where scientists talk about the various merits of various weighted averaging schemes that I don't understand. But never, ever do they mention scale or data size problems. This person is also a first-time contributor, which is also nice. I have no idea who this person is. They just showed up. So it's really a win for people just generally talking about science once science is available for everyone to talk about and interact with directly. Success, there's no full-time staff. I mean, some of us tweak things from time to time. Sometimes things break, but no one's really paid to do this full-time. And thanks JupyterHub and people who work on JupyterHub for making this very easy. Other domains have started taking this on. So microscopists, genetics people, astronomers have all started looking at the same technology stack. It's really independent of atmospheric science. It can be used in a variety of different situations. So to sort of finish, there's some challenges and opportunities. There are too many scientists and not enough non-scientists. So again, my call to action to all of you, please check out, we have an issue tracker. It's very open and welcoming. People show up every day saying, hey, I'm this person, I have these skills, I have these needs, how can I fit in? There's be a link at the end. If you have some interesting thoughts, design skills, ability to make websites, we're really lacking on those. We can write Fortran code and do science. That's kind of it. Some other challenges that are interesting, managing software environments and user permissions has been a tricky challenge. Cloud native data storage for scientific data formats, it's a really interesting question. There's a lot of support in the open source community for business intelligence cases, Parquet file formats, SQL databases, but not a whole lot that handles this sort of other need of large raster data sets. And that's it. Great. Thank you so much. I think we have about 5 minutes for questions. If you want to stand up behind the mic in the center, happy to take questions. Come on, somebody. Yes. Thank you.
Thank you for the great and inspiring talk. I was wondering, so you were mentioning that there are petabytes of data being published on geoscience, and you are basically crawling these websites or perhaps querying this data. Are there tools that you think will be able to make it easier to share this data? For example, I found in science and academia, usually when a paper is published, the data that accompanies this paper is not always shared, or it is shared but in a very difficult to access platform.
Yeah, so the really nice thing about a lot of these data sources is that they're coming from government organizations, and they actually have a mandate to share the data. Mm-hmm. So historically, if you look back a few years, all this data was on either supercomputing centers that anyone could hypothetically get an account to and do some work on, or they were served in national data centers, which had some sort of difficult to access API. What we're seeing is a lot of government agencies like NASA or JPL are now pushing data onto the cloud. They're just dumping data onto AWS in sort of public access buckets. I think AWS is funding the storage. And this is great, except that we don't have really a good computational mechanism to query and access that data. We can access the data if you can use S3 or another cloud storage format, but we're sort of trying to build a computational complement to S3 to do that analysis. So I would say it's actually the data is becoming very public and very easy to access. There are data catalogs you can look at on a few different government agencies that will have this access to a bunch of kinds of data.
Cool, thank you.
Hi, so I've started trying to play around with JupyterHub at my company for some of our researchers to use. And one of the things I kind of ran into right away was it was a lot more difficult for people to kind of share notebooks they had with each other because you can't copy and paste the link and send it off. Is that something you've run into with the scientists working on this platform, and how are you thinking to address that problem?
Absolutely, it's definitely been a problem. People have analyses, they want to share them. They used to email their notebooks back and forth. That's sort of not the right way to do things. What's the right way? We don't have a good answer. So no, that's a pending question we're trying to address. So interestingly, so I'm going to take off my open source hat on, put on my Anaconda evil enterprise hat. I never understood enterprise software that Anaconda was building until I worked on this. And it handles managing sharing notebooks, handles environments and building software systems. It's like all the problems that I now have, I now want to buy enterprise software for. So one answer is to pay a lot of money to a company. And Anaconda has many competitors in this space. But it's an active problem that many companies are trying to address. And now we're trying to address it in open science as well.
Great, thank you.
I'm going to take off the enterprise hat. Put it back on open source.
So I'm not an oceanographer, but I am a NASA research scientist, and these all sound like really wonderful tools. And NASA is pretty good at making its data available for other people, but internally, allowing our researchers to do research on the cloud or someplace else is very challenging for all of the security reasons that make our lives difficult. And my question is, have you already established installation of these on government hardware for internal government use?
Yeah, definitely.
Okay.
So Dask has been around for a while, and it's very popular in more traditional high-performance computing clusters.
Okay.
If you're interested, I recommend looking at a project called, Dask Job Queue, which is a nice way to set up Dask on a variety of more traditional job schedulers like SGE or Slurm or Torque or LSF,
Okay.
if one of those sound familiar to you.
Okay,
Uh,
yeah.
so yeah.
That makes my life easier if someone else has already done it. I can point.
Yeah, and you should also go on to the Pangeo GitHub tracker.
Right.
Put the link back here, and you'll find that many people are running on a variety of different clusters, maybe already the one that you're working on.
Okay, great. Thank you.
Yeah.
Hi, Matthew. I found a lot of documentation for Dask on how to use it and all the power it has. Where I'm having difficulties knowing how to set it up for my company. Like, what is the proper way to set it up? And I don't find much documentation either. Can you point me to some resources for that?
Yeah, so if we go to the Dask documentation, at the top there's a deploy link. So it'll take you to the main deploy documentation. There's a variety of different options based on if you're running on a single machine. Dask works very well on your laptop for just out-of-core data work. Or maybe more complex things like SSH or high-performance computers, like with a NASA person, or Kubernetes, or other sort of options. So this is where I would recommend starting. Most documentation for Dask is at dask.pydata.org. I'm also at the Anaconda booth a fair amount today if you have other questions and want to chat.
Okay, thank you.
I think we probably have time for one more question, and I should probably yield the floor.
Really quick, for those of us setting up Dask deployments on-premise at a company, it sounds like Kubernetes is like the right orchestrator or like the preferred orchestrator. Is there like a preferred data source, like a database or a file format with which Dask works best?
Yeah, so Kubernetes is not necessarily preferred. I like it, but usually people already have a system set up, and
Okay.
Dask usually works with that system. So there's a variety of ways to set up Dask depending on your needs. In terms of data source, I say it depends a lot on the kind of ways you're planning to use Dask. If you're using Dask data frame, the sort of scalable big pandas data frame, you might use Parquet or ORC format. If you're using Dask array, you might choose HDF5 or something else. But Dask is also used with a variety of other more custom systems. I think maybe Dask's main attraction for a lot of companies is its flexibility, its ability to work with a variety of different, more custom in-house systems. So,
Thank you.
great. Thank you all so much for your time.